Why should we recognize as good as any other?
Because they are high school
We still might
students in their
animal trackers like every day.
Do you want to go? Now we're even.
All right. A few things before we start our next section. Everyone got your derivative review sheet, right? Okay. This is our pass-fail number 3 because our third quarter is coming up. This is just a comprehensive review of like everything dealing with derivatives that we've done since like October. Now, these are meant to be very quick type problems, so you're not going to have any of those like word problems with related rates or like free response type involved questions. These are going to be fairly quick. Okay, so go ahead and try some of these out. Solutions are already online. I'm thinking that we're going to have our first go at it by the end of the month. Okay, so in a week or two, we'll have our first pass-fail, and then you'll have till the end of the quarter to make sure you pass it. For our current quarter pass-fail, you know that today is the last day of the second quarter. So technically, today's your last day to pass our second quarter pass-fail. They are not pulling grades, though, until next week, so I can give you until Friday. Okay, you're welcome. Okay, so that'll give you a few extra days. Okay, maybe let's make this be a learning experience and maybe not wait till the last moment to try to pass it. Okay, you're not the only one in that boat.
Yeah, I'm not the only one.
Okay, I still have some other people that need to do it. All right, so timing-wise, pass-fail by the end of the month. We're also going to finish this Unit 5 by the end of the month, so anticipate a quiz and a test coming up in a few weeks as well. I was crunching some numbers yesterday, just trying to get our schedule lined up for the rest of the year, because I don't know if you realize it or not, but teachers don't have a day off until spring break. Like, we're here every day. You guys have a day off here and there, okay, but we don't have off for like a solid 3 months. So when I'm looking through where we are now and where we need to be, if we can stay on track, which we have been all year, actually sometimes ahead of track, I'm thinking that we're going to be able to finish all of our required content before spring break. Maybe like a day or two before spring break.
And then can we just party?
Not quite, okay? That's actually going to leave us with about 2.5 weeks of review time until the AP exam. Now, when I look at those numbers, that's crazy in my mind because I've never had that much time to review. And we started this year, I think, a little later than last year. We had a longer Christmas break this year than last year, and I have more review time this year than I had last year. So I don't know how that happens, but somehow it did. Yes?
So what do we do after like the AP test?
After the AP exam, okay, so the AP exam is May 5th. I don't know when seniors' last day is. It's towards the end of May, I think. So that leaves us with 3 weeks or so. You're going to have that time to do your fourth and final pass-fail. So you can do it every day in here if you wanted to try. If you still don't get it, okay.
We've already taken it.
We could, if you want to organize that, but you are going to have a partner project to do. Okay, so you're going to have about three weeks to do that. Okay, but other than that, we're basically done once the AP test is over. Probably not. Probably not. Okay. Anyway, make sure you have a calculator today because we're definitely going to need it. And open up to page 309. We're going to be dealing with particle motion more today. We're actually going to bring it back a little bit more in Unit 6, but we're going to focus on distance today. We haven't really talked about distance. We've done acceleration, we've done velocity, We've talked about position, meaning where a particle is located, but we haven't really talked about how we can calculate distances, like how far the particle has traveled. So before we actually get to distance, though, we have this example in 309, which is going to be kind of a review of some of the things that we've talked about so far with particle motion. So they tell us that the graph represents velocity, and our units are meters per second, and the particle is moving along the x-axis. So the particle is only moving left or right, but as time goes on, this graph is giving us different velocity values for the particle. All right, so let's check out the first one. We're going to have to add in a little word here because I forgot to type it in. At what values of t does the particle have no acceleration value on the interval? If you don't have a value, that basically means you're undefined. So if this is the graph of velocity, can we try to think about where we should be looking on this graph to determine where there's no value for acceleration? What do you think, Cole?
When it equals 0. So,
Here?
yeah.
Okay. Why?
Well, no, like all the roots. When it crosses the x-axis.
That's where velocity is 0, because this is the graph of velocity. It's 0 here, 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 here. But it's asking for when is acceleration essentially undefined. How is acceleration related to velocity? It's a slope, aka derivative. So this is basically asking us where is the derivative of velocity undefined? Where's the slope of this graph undefined? What do you think, Austin?
The hard edges.
Hard edges. So sharp points. Time equals 1, 3, 6, 8. Okay. Now, we've also discussed how endpoints don't have a slope or derivative value, but we technically don't have to include those because notice how 0 to 10 is an open interval. So you don't need to count 0 or 10 as the endpoints. So we'll say these values because v of t, the information they give us, has a hard edge, sharp point, cusp. Yeah?
What's the difference between like acceleration as being 0 and having no acceleration? Like having it undefined?
Okay, so the wording has to be pretty specific. If it said where the particle has... If I took out that word value and it said no acceleration, I think that's where it can be a little vague because no acceleration could mean 0, but no acceleration could also mean undefined. They'd have to be pretty specific. I think they would say, where does it have an acceleration of 0 to specify that interval? But I wanted to throw in value because that can signify if it's defined or not. Okay, so the wording I think would have to be pretty specific, if that answers your question. Okay. All right, let's try the next one. Express acceleration, which we've already mentioned was the slope of velocity, as a piecewise defined function. You actually had a similar question on your winter packet, if you remember that one or not. Okay, can we figure out what the acceleration function might look like? They already kind of clue us into piecewise, so we're going to have different equations or values in different intervals. Can we find the slopes? What about the slope of our first interval? 3, okay. We'll come back to the intervals in a second. What about the slope of the next line? Negative 3. Okay, if you do like rise over run. Slope of the next 0. All right, I got to write a little smaller here. So 3, negative 3, 0. Next line, positive 3. And then the last one, negative 3 over 2. You go down 3 units, right 2 units. Okay. Okay, so we can find the individual slopes, but piecewise functions have a second part to them where you have to kind of write the intervals where that shows up. So this first line shows up from 0 to 1 with times in between. And the inequalities always point to the left, like t is trapped in between those. The question is if we need to include bars on any of those inequalities.
No, I missed this on the test.
You missed it. You missed it on the winter packet. Why is it a no? Do we have acceleration at 0? Do we have a slope at an endpoint? No. So no bar. Do we have an acceleration at 1? No. Sharp point, right? That's what we said in the previous question. So no bars for those. The next slope goes from 1 to 3. With kind of the same reasoning, we have a sharp point at 1 and 3. 0 goes from 3 to 7. 3 and 7 were sharp points, or sorry, 3 and 6 were sharp points. Next interval, 6 to 8. Those were sharp points. And last interval, 8 to 10. 8's an endpoint, 10's an endpoint, so you can't, or 8's a sharp point, 10's an endpoint, you can't count either one of those. Okay, so no bars. We doing okay? So far? Okay. For what value of t is the particle moving to the right, to the left? Justify your answer. How can we know which direction we're traveling in? Yeah?
Positive, negative.
Positive or negative what?
Velocity.
Velocity. Okay, velocity is speed with direction. Okay, so if we're moving to the right, we got to figure out where we have a positive velocity, and if we're moving to the left, where we have a negative velocity. All right, so this is the graph of velocity. We can use that to our advantage. This graph is positive from 0 to 2 and 7 to 10. So we'll say because v of t is positive and we're negative from 2 to 7. So we'll be traveling to the left. All right, find the average acceleration of the particle on the interval from 1 to 8. So we already know that acceleration is the slope of velocity. And if we want an average slope, that means we got to figure out the slope between 2 points. So our interval is from 1 to 8. So what would the slope of the line be if you connected those 2 points? Zero, flat, right? They have the same height. Okay, so we'll say average acceleration is 0. Can we throw in units? Meters per second squared. Okay, acceleration is a squared unit. Okay, meters per second squared. It says show your work. We didn't really show anything, but maybe we can explain. What do you want to say? Because
Y value doesn't change.
okay, the y values of the endpoints are the same. They don't change. Isn't that technically Rolle's theorem? Endpoints have the same height. The derivative or the slope should be 0. Okay, makes sense. All right, I need you to throw in one more at the bottom. Can we see that? At what times or time does the particle have the fastest speed? Again, this is the graph of velocity.
1 and 8.
Why?
It's the highest point on the graph.
Okay, so if this is the velocity, the fastest speed would be the highest point. So 3 and 3. What do you think, Griffin?
Also, 3 and 6.
Why?
Because like they're min values, but it's just like the negative is the direction, so it's still 3 meters.
There we go. Okay, so remember, velocity tells us two things, speed and direction. So this point right here is telling us we're traveling at 3 meters per second in a positive direction, or in this case to the right, because it's positive. But this point is telling us we're traveling 3 meters per second to the left. Notice how they're the same speed, they're the same number, okay, if we don't count the direction, because they're just asking us about speed. So we're definitely traveling the fastest here at 3, the fastest is here at 3, but we have some other ones down here. And not only is 3 and 6 have that speed of 3, but also everything in between them. So we might have to write that as an interval from 3 to 6. So at this point, at this time, and any time in here, okay, from 3 to 6, we have that fastest speed. So we'll say because maybe the absolute value of velocity, like if we ignore the positive or the negative, if we just look at the number itself, is the max. Okay, we have 3 for both. What if I changed this part that dipped down more, like that? Maybe this was like -5. This would be the fastest speed, even though it's a minimum. Okay, you're traveling at 5 meters per second to the left, whereas up here you're traveling at 3 meters per second to the right. So if you're just looking at speed, you just want the number value. The sign doesn't really matter. Does that make sense? Okay, a little tricky. All right, good review. So let's go ahead and talk about distance on the next page. There's technically 2 different types of distances, and again, if you're in physics, this might sound familiar. We have what's called net distance versus total distance. And can you think about perhaps the definition or the difference between those 2 terms? You might know net distance as a different phrase, yeah?
I'm not really sure, but it feels like net would be like kind of the overall, like even if you went like back and forth, like basically like your final where you are minus your starting point.
There we go. The distance between a beginning point and an ending point. If we write down that definition, do you know net distance as a different phrase? Maybe you've used it in physics. How far you are from where you started? Displacement. So I don't care how many times you change direction. We're just worried about where you start, where you end, and the distance between those 2 points. Okay? Total distance, on the other hand, is a little different. How can we calculate total distance? Yeah?
Even if you're like backtracking and like going left and right, just like the total amount of, you're going to use the word total distance, but I don't know.
Absolutely.
Thanks, Christian.
Well, let's maybe do an example. So let's say I start here, I travel 5 to the right, and then 2 to the left. What's my displacement? 3, right? What's my total distance? 7. How'd you get 7? Atom. Okay, so the sum of the distances traveled. Does traveled have 2 L's? It's math class. Traveled in any direction. I'm going to say it's 2. All right, so this kind of, we have technically 2 different types of distances, the displacement, the net distance, or the total distance. What if a particle, though, is moving in the same direction the entire time? Yeah?
The net distance is equal to the total distance.
The net equals total, okay? So the only way the net and the total are going to be different is if you change a direction at some point. Okay, so we might have to be careful about if that happens or not. Okay, so net equals total. So let's go ahead and think about how we can find net distance, how we can find total distance, at least mathematically. So we said it's the distance between the beginning point and an ending point. In terms of our particle motion functions, position, velocity, acceleration, of the three, which one would give us a point location? Does position tell us location, velocity tell us location, acceleration tell us location? Position. Okay, so we need the position at a beginning point, maybe we'll label that A. We need the position of the ending point, maybe B. And what do you have to do to those two values to get the distance between them? Subtract. Okay, now distance is never negative. Okay, direction could be, but distance is not. So if this value happens to be negative, we're just going to ignore it, meaning take the absolute value of it. Maybe we'll write distance never negative. Okay. All right, now total distance on the other hand, let's assume we do have that changing point. So we'll say we change direction at maybe x equals c. Okay, how can we find our total distance? Remember, we let A be the beginning point and B be the ending point or ending time. How can we figure out total distance? You start at A, maybe we're moving to the right, and then eventually I change direction. So I'm going to have to stop a calculation at this value. I'm going to have to figure out how far this was. So I'm going to need P of A minus P of C, okay, where we stop or change direction. So I got to figure out that distance. And then if I change direction, I got to figure out how far I go the other way. So in this case, that would be P of C and P of D, where I end my movement. And that's another distance. So if, let's say this is how much I move right, this is how much I move left, okay, kind of my individual displacements in terms of my direction. So what do I have to do to these to get my total distance? We said add them together. Okay, so if you have a change in direction, it's going to be a little bit more of a calculation because we have to separate those different distances. How much we move one way versus how much we move another way. Okay, so we're just going to take a look at some examples and get used to the wording, like are they asking us about net, are they asking us about total distance, and how we can do those calculations. All right, so the bottom, the position of a particle is given by this function. Okay, so we have position measured in centimeters. Find the net and total distance, so we're actually going to do both, that the particle travels from 1.5 to 4 seconds. Okay, maybe we'll try net first, aka displacement. We said that's pretty simple. We just need our beginning location minus our ending location. So how do you want to figure that out?
Find P of 1.5 and find P of 4.
There we go. All right, so we'll do P of 1.5 minus P of 4. So this is where you might need your calculator. So let's see. If we plug in 1.5,
It's going to be 6.
5.25, that's what I got. And then if I plug in 4, that was actually pretty close. I got 64.
Yeah, it's really cool. Really cool.
All right, so this is our position where we start. 64 is our position where we end. And if we subtract those, we traveled 58.75. But I don't care if it's negative or not because it's just a distance, okay, how far you actually travel. So 58.75 centimeters. Okay. So this is just what we calculated was beginning and ending. Okay, we don't really care, at least for net, if we change direction anywhere. However, for total distance, we do want to figure out if we change somewhere. So how can we figure out perhaps if we change direction at some point between 1.5 and 4? We could. Okay, if we take the derivative of position, that would be velocity. So 6t squared minus 12t plus 8. And what's the velocity if we're changing direction? If you're moving to the right and then you have to change moving to the left, it's 0, right? Because don't you have to momentarily stop? Because you're only moving left or right or up or down. So you have no choice but to stop. It's not like you're going around a bend. Okay, that's something completely and totally different because you're only going in a linear path. So let's see if this equals 0 anywhere. Can we factor it? Take a 2 out. Oh boy. A times C is 12, B is negative 6. Two numbers that multiply to 12 but add to negative 6. Can we factor? Okay. Can't factor. If it's a quadratic and we can't factor.
Put it on a graphic.
You go on your phone?
Let's do the quadratic formula.
Your graphic calculator.
We'll do quadratic formula. Okay. I'm going to ignore the 2 because we factored that out. We need the opposite of b, so that'd be 6, plus or minus square root b squared. Negative 6 squared is 36, minus 4 times a times c. 4 times 3 times 4, 48. All over 2a. 2 times 3 would be 6. What's going to happen if we solve? Why?
Because there's going to be a negative number of radical.
We're going to get an imaginary number. So what's that telling us about velocity? It's never 0. It never changes positive to negative. You never have that change in direction. Okay? So we'll say never equals 0. So if velocity is never 0, then this particle is never changing direction. So if it never changes direction, what's our total distance?
Same as the net.
Same as the net, okay? So total distance, same as net, because particle never changes direction. Looks good. All right,
Nice.
let's try another one. The position of a particle is given by a function. All right, so we'll box it in. Units this time, feet. Find the net and total distance, so same type of question. We're going from 0.5 minutes to 1.5. All right, net. The distance, or difference, if you will, between where we start and where we end. So p of 0.5 minus p of 1.5. I don't care if it's negative, so I'm going to take the absolute value of it to get rid of the negative if there is a negative. Can we use our calculator? I got negative 1.28172 if I plug in 0.5. And then I got 8.08554 if I plug in 1.5. All right, so subtract the 2. Ignore the negative if it's negative. 9.367. Chop it 2 or round to 3, either one. Round to 3, okay. and units are feet. All right, so from where we start to where we end, this is how much we've traveled in terms of displacement. Now for total distance, we got to figure out if we change direction anywhere, because if we do change direction, then this net distance is probably going to be more, because we're traveling more than what we actually did between the beginning and ending. So we got to figure out, where do we change direction? They give us position. We got to analyze velocity, see when that's 0. So can we take our derivative? How do we take the derivative of e to a power? E to the power times the derivative of the power. Good. All right, and then we'll have minus 8 on the end. So we're going to set this equal to 0 and try to solve for t. I think we can do that. If we add the 8, divide the 2, we'll get 4. Move the e over, becomes a natural log. And then we'll divide by 2. So on our calculator, we got to type in natural log of 4 and then divide that by 2. .69315. All right, so this is where velocity is 0. Do we change direction at this spot?
No.
Let's see. I can walk to the right, stop momentarily, but couldn't I keep going to the right?
Yes.
Right? Wouldn't my velocity be 0 at this spot?
Yes.
So just because I'm 0 doesn't mean I'm changing direction.
Yes.
Okay? So we got to test it. Maybe we'll use our sign chart. We got to figure out if we change a sign, positive to negative. So v of t, let's see, according to our interval, we're just going to go from 0.5 to this 0.69315, and then this same point to 1.5. So let's see. Pick a number between 0.5 and 0.69315. 0.6. Okay, we're going to plug it into the derivative. So 2e to the 2 times 0.6, and then we got to subtract 8 on the end. Looks like that's negative. So on this interval, we're traveling to the left. Velocity is negative. And then pick a number between 0.69315 and 1.5. 1. If we plug in 1, 2e squared minus 8, positive. So we do actually change direction. All right, so for total distance, kind of running out of room here. Total distance, we got to figure out how far we travel on this interval where we're going left, and how far we travel on this interval going right. Maybe I'll write that down here. I'll put D for distance. So let's go ahead and plug in 0.5 into position, 0.69315 into position, and we're going to subtract those to figure out how far we travel on this interval. E squared times 0.5. All right, so I have my two numbers. If I plug in 0.5, if I plug in 0.69315, and then I got to subtract those together, or basically find the difference between those. So let's see. 0.26346, if I ignore the negative. Okay, so that's my distance traveled on that interval. We're going to do the same thing for the other interval, how far we're traveling to the right. All right, so I have my two numbers. I'm going to find the difference between those. 9.6307. All right, so I officially know how far I travel to the left, how far I travel to the right, and if I want my total distance, we got to add those together. So plus 2.26346. 9.894, chop it at 1, round it to 2. We doing okay? Are we okay with the difference between the distances? Net distance, total distance, they're a little different, okay? We'll stop there for today. We'll try the next one tomorrow, and then we'll take a look at kind of 2 free response type questions that have been on AP exams before.